Welcome to Wireless Future. I'm Emil Björnsson, and just as in the last episode, this is going to be a conversation with Eric Larson. How are you?
Oh, good, Emil. How are you today?
I'm perfect. So it will be exciting to continue these podcast and videocast. And today I was thinking that we're going to talk about this wireless future that we are heading into, where everything starts to be wirelessly connected. And we are sort of relying more and more on this different wireless connectivity and all the apps. So some weeks ago, I was dropping off one of my kids at an activity and I realized that I forgot my phone, which meant that I couldn't even pay for parking anymore because everything is sort of relying on that we are wirelessly connected all the time. And I was thinking then that what are the consequences that are not so good with that kind of development? So we see all the convenience, but are there any problems, sort of security concerns?
So, I mean, you're entirely right. We're building a society that relies increasingly on infrastructure for wireless communications. And that also exposes us to a number of new threats. In wireless specifically, there are really two main kinds of threat. Number one is eavesdropping, that somebody is like listening to a connection that's supposed to be secret or private. And the second is jamming and spoofing, which means someone is actively transmitting something in order to disrupt the communication link or pretend that someone else is you and thereby gain access to like your services from the network. So these are threats that are all due to the open nature of the wireless channel. I mean, if I put up a wireless link here with a transmit antenna and the receive antenna, then the transmit antenna sends something out, and anyone in the room here in principle can receive that signal, right? And anyone in the room could concurrently transmit something else, and my receiving antenna would have no chance of telling whether, you know, the signal and pinging there comes from the legitimate transmission or whether it comes from someone else. And just as you said, I mean, this is a potential threat to...
Yeah, it sounds troublesome.
Yeah.
So what more specifically could these kind of properties be utilized for if someone wants to sort of affect us in a negative way?
Right, so perhaps jamming attacks are the simplest. I mean, and well, my favorite example goes back 20 years to the 2001 EU summit in Gothenburg in Sweden, where the police had 700 officers on the field, and some of the demonstrants used equipment to jam the police officers' radio communications equipment, to the point that the commander in charge could not reach any of the officers on the field. And I mean, this was done using extremely rudimentary technology and done by folks who probably had not much idea about wireless to start with. So, I mean, just imagine what you could do if you really wanted to cause harm for real here. And I think we have to understand this also in the context that equipment for jamming, for example, I mean, equipment that maybe 30, 40 years ago used to be military grade, cost millions of dollars, is now today things that you could buy off the internet for no money at all. So all this technology, I mean, air quotes technology for jamming and disruption of wireless links has a potential mass market that nobody knows where this could be going if somebody really wanted to cause harm for real.
So are these products that you can buy commercially in an open way, or is it something that is forbidden to sort of own?
Well, I'm not quite sure. I suppose it depends on the jurisdiction whether it's forbidden to own, but I think most parts of the world is definitely forbidden to use. I mean, if you can't, it's not allowed to transmit in spectrum that you don't own, right? And to some extent, I mean, equipment for jamming is still like military grade, but there is a black market for it. So you can buy it if you really want. But it's also true that a lot of equipment for like just research, experimentation with software-defined radios, for example. And we had in my at the university, we had a student project some years ago where we used software-defined radios to listen to GSM signals, and it would be equally easy, I mean, to transmit GSM signals. We didn't do that, obviously, because it'd be illegal, right? But in principle, you could do it with that sort of equipment, and we're talking about equipment that cost $1,000 or less here. Yeah.
Yeah. So I've heard about that there are these two categories of attacks, the active and the passive attacks. So are these mapping to these two categories that you mentioned before with eavesdropping and jamming?
Right. So passive attack basically means you listen, right? You try to eavesdrop. You try to gain access to someone else's data by overhearing or just listening. Active means that you transmit yourself in order to disrupt a communication link, or in order to pretend that you are someone else and thereby would gain access to, I mean, whoever that other person's data. So that is the distinction between active and passive. And in a way, I mean, passive is simpler because it doesn't require a transmitter. Passive also means that nobody can discover that you're there, right? If you're active, then you transmit something, so others could, in principle, locate you and see where you are.
I see. So let's go through these two categories in a little bit more detail. So we can start with the passive case, the eavesdropping. So I'm having the impression that whenever you send some data over the internet or so that is important, you sort of try to use some kind of end-to-end encryption protocol. So you encrypt it at the transmitter, and then when you receive it somewhere else in the world, you decrypt it. And then the signal could, of course, float over the internet in cables, but it could also go wirelessly. Does this thing that the signals, even if they are encrypted, floating over the air, does that create some kind of additional problems that we don't have when we are sending it over cables?
Well, I mean, for one thing, there are more potential eavesdroppers in wireless, right? Because if you want to eavesdrop on a cable, you got to either cut the cable or you're going to get really close to it. But in a wireless link, in principle, it's enough that you're somewhere in the vicinity. But now that said, I mean, as you stated, right, most, if not all, of the wireless communications today is encrypted. And that encryption is extremely secure, typically. I mean, it's amazing what this cryptography technology can do for us. So I think the eavesdropping threat is really, less of a real threat unless we are dealing with actors that have access to extremely fast supercomputers or side knowledge about the system somehow so that they could break the cryptos. But
so would it be fair to say that for criminals of the sort of regular kind, it won't be a problem if it is the states, organizations that are anyway conventionally wiretapping in the wired setting, they would also be able to decrypt wireless signals if they have enough resources?
Probably. I mean, breaking cryptos is extremely hard, right? So the encryption itself typically probably is not the weakest link here.
I heard about something called physical layer security. So I guess this end-to-end encryption is some kind of application layer encryption or security. So what can you do in the physical layer to try to actively make it more secure?
Right. So I mean, as you said, I mean, conventional encryption works on the bit stream itself, right, on the zeros and ones, and then intermingles the zeros and ones and adds security through like data processing or digital processing of those bits. Physical layer security, on the other hand, works on the actual electromagnetic signals that propagate over the ether. And physical layer security itself is actually a whole family of techniques. To give a couple of examples, number one is beamforming for physical layer security. So here the idea is that, well, if I'm the transmitter and you're the receiver and I have a large array of antennas, I can beamform and transmit power only in a small, narrow, angular window so that it reaches you, but it hardly reaches anyone else. So if an eavesdropper is located a bit away from you, then the eavesdropper will receive so little power from my transmission that he won't be able to decode or I mean, pretty much hear anything. Example number two is key generation. So pretty much every cryptographic algorithm in use today relies on the two parties communicating to have some common source of randomness. I mean, typically way it works is that I know some secret random number or code or key, and you happen to, through some mechanism, you have obtained the same secret key, and then we can use this secret key to cipher the messages that we send to one another now. So now, in order for us to generate these keys, we need a mechanism for that, and public key cryptography can do this for us. And there's an additional layer of, say, security in this key generation. It has been suggested to utilize physical layer properties. For example, the fact that if you and me talk to each other wirelessly, then, well, the channel between us, so the actual channel impulse response, I mean, the way that the electromagnetic propagation environment looks between me and you is reciprocal. So you see the same channel response to me as I see to you. However, anyone else here in the room or somewhere else would see a different channel response. So only you and me would know this channel response, and that way we could use that to generate a secret key that only the two of us know, but nobody else knows. So these are two examples of physical layer security.
There seems to be a whole wealth of methods here. So I have this impression that sort of when we move to digital communication from analog communication, that is sort of automatically providing us with some kind of benefit here, because as you were mentioning in the first example, we tried to use beamforming to make sure that we sort of have a stronger signal at the desired receiver than at any eavesdropper. And if we are then encoding our information with digital communication, there is this concept of adaptive modulation and coding. We try to look at, okay, how good is the channel? Then we try to squeeze in as much information as possible. And as long as someone else is having a much weaker channel, they won't be able to decode it because their channel didn't support this. So would it be accurate to say that there is some kind of built-in security against eavesdropping already in any digital communication system?
Yeah, in a way, I mean, but who knows? I mean, if you look at a wireless link and the transmitter uses just enough power so that the receiver can decode, right? Or selects just enough modulation scheme that the receiver could decode. But what if the eavesdropper is closer and has a better channel? So in that respect, it doesn't really help. But it's certainly, on the other hand, true that you could, with digital transmission technology, you could apply other countermeasures, especially to jamming.
So let's move into jamming then. That was sort of the active types of attacks. So what are we doing more precisely in the jamming situation? What is the problem?
Right, so with active attacks, there are really two kinds of active attacks. One is jamming. Jamming just means that you want to disrupt the communication link and cause it to malfunction, right? And the other is spoofing. Spoofing is more sophisticated. In spoofing, it's more like the spoofer transmits something that makes the network think that he is someone else. And jamming might be the simpler of the two. But it can be also extremely harmful. I mean,
So what can you do to sort of counteract jamming? I guess the military must have standard ways of trying to deal with jamming in their kind of systems in military situations.
Right. Of course, I mean, jamming has been like A or D problem in military communications for as long as there has been radio communication, wireless communications, right? I think the short answer to your question is spread out. I mean, spread over large bandwidth, and you can do this through direct sequence CDMA or through frequency hopping or through OFDM with coding over frequency domain. So spread out over frequency, spread out over time if you can afford it. Typically we can't afford it because we have latency constraints, so we can't like spread the message out over too long time. And focus in space. I mean, if you have an array of antennas at your receiver, say, then make sure to steer the array to look into the direction where the transmitter is located and nowhere else, so that you won't receive, potential jamming signals that are coming from elsewhere.
So it is a bit like saying that the jammer have a total amount of power that they can use to harm you, and you try to sort of force the jammer to spread it out as much as possible over frequency domain and over space, so that it will hit you, and then the piece that actually is hitting you becomes smaller and smaller.
Right, yeah, that's a good analogy, I think.
Yeah. So are we doing any of these things in the cellular communication systems?
We definitely do. We spread out over bandwidth, right? Most of if you look at 5G, for example, the systems use huge bandwidths. So we do that. On the other hand, these systems and standards tend to be vulnerable in another but related aspect, namely, all these systems use control channels. Control channels are like supporting channels that carry rather little information, but very important information. Information on how to, for new terminals to join the network, telling them how they should act, which frequency carrier should they transmit on, when should they send something, what should they send when they want to join the network, for example. And also in closed loop operation, in an ongoing communication link, there are pilot signals sent all the time. For example, in reciprocity-based massive MIMO, there are pilots on the uplink sent by the terminals, and these pilots are used by the base station to estimate the channel impulse response. And as it turns out, if someone hits these pilots and transmits jamming, which is then focused in time and frequency to hit precisely on these control channels or on these pilot signals, then that can cause a lot of harm, much more harm than just transmitting blindly, like trying to jam the whole thing. So an effective jammer here should really hit the control channel, or try to hit the control channels, or hit the pilot signals.
So we have built protocols that have certain pieces of them that are essential for the rest of the transmissions to work out. So if you hit those ones, you are sort of harming the entire system.
Yes.
I guess one example there would be this type of, when a user would like to connect, it sort of speaks up at a certain time and say, I would like to transmit, can you please schedule me for transmission? And if no one else is talking at the same time or you are sending a signal, then the base station hears you and schedules you. And if someone is constantly screaming on those tiny channels, then it will be hard to be heard.
Right, see, that's the point. The control channels occupy a fairly small fraction of the frequency spectrum, and it is possible, either it might be known a priori, or at least it's possible to figure out where in the frequency spectrum are these control channels, so that a somewhat smart jammer would know exactly where to strike.
Okay, so we have talked about massive MIMO in previous episodes as sort of one of the key new things in the 5G standard, for example, or new deployments. Do we, with massive MIMO technology, get some kind of improvement in terms of reliability against jamming, or is it just as bad?
See, at the surface, it might seem that massive MIMO technology would be inherently a lot more robust to, say, jamming attacks, right? Because if you have a large array of antennas, you can form narrow beams, and if someone is trying to jam you, you could filter them out by placing a spatial null in the direction where the jamming signal comes from, and that way just filter it away. Reality turns out to be a little more complicated, and the reason is that because of these pilot signals that we talked earlier, that when the massive MIMO array communicates with terminals, then the terminals first have to send pilots in order for the base station array to learn where they are, so that the base station array subsequently can form a narrow beam to the terminal. However, when the base station array receives these pilot signals, then it doesn't know in what direction to look. So it kind of has to look omnidirectionally. And that way it'll be susceptible to jamming signals that come in from any direction. So I think the short answer is that well, potentially massive MIMO technology could be made a lot more robust to jamming, but the canonical, like, standard way of operating reciprocity-based TDD massive MIMO, it isn't really. I mean, for this reason that the reception of the pilot signals doesn't filter spatially. So, and that's really the critical point of the, or part of the transmission protocol.
I see. So would it be fair to say that then the massive MIMO technology could be more robust against the passive attacks because of the directional transmissions, but not necessarily against the active attacks because you still have this sensitivity in terms of the control channels and reference signals?
Yeah, I think that's an accurate assessment. I mean, I wouldn't think that passive attacks are really a main problem because cryptography is so good. And obviously, I mean, if you have good cryptography, if you add additional security on top of that in terms of, for example, the capability of transmitting in very narrow beams, well, that's only good, right? But for the active attacks, well, this is not entirely known, I mean, firmly. So it's like a bit of an open research problem to really figure out fundamentally, is massive MIMO technology more robust or not? And if so, how should it be operated in order to really get this robustness? But if we look at like canonical TDD reciprocity-based massive MIMO, the way it's described in the textbooks, it's not more robust to jamming attacks than any conventional system. Well, unfortunately so, yeah.
Okay, so I have one sort of idea that I would like to test with you. So I guess both of you and me have been sort of promoting that we should build these massive MIMO technologies based on digital beamforming, where you sort of have all of these antenna elements, and then you are able to control each of them separately. You sort of sample their signals, store them in a computer, and then you process it in a digital domain. But then there is this other more traditional approach where you build this type of things in analog. So you sort of having analog circuits that are putting together different antenna element signals first, and then you sample the combined signal. And there are always good reasons to use digital beamforming in terms of being able to sort of process the signals in different ways and so many users and so. But I'm thinking whether there is a drawback when it comes to jamming, because if we are first forced to take every element in our array, sample the signal, and then we need to process it afterwards. Then if every sample is very, very bad because we sort of have added up a lot of these jamming signals there, then it might be hard to do anything. While an analog system could sort of steer in the analog domain with infinite precision your signals from one direction and ignore directions where the jamming is, and then you sample after you have sort of already gotten rid of the jamming. Does that make sense to you?
Oh, yeah, so that's a nice line of thought. I mean, so you're suggesting that with analog beamforming, you kind of like spatially pre-filter the signal before it enters the digital processing, and that way the digital processing itself would not have to be as robust to jamming. Yeah, it's very possible. I mean, I think, if we look at digital first, right, then the way digital front end works is they have analog filters that cut out the interesting part in the frequency domain, and then you have an AD converter to take the samples, and the AD converter has a certain resolution that we measure in terms of number of bits. And after the AD converter, we get basically a string of zeros and ones that enter the digital processors, right? And now if we have a strong jamming signal, then in principle, I mean, according to like MIMO textbook theory, if it comes in from a different spatial direction, we could filter it out through spatial processing. I mean, there's all the zero forcing methods and all that, right? But this, of course, assumes that we have enough dynamic range in the actual digital signals that we process. And that, in turn, means that the resolution of the samplers and the AD converters have to be sufficiently good. So the resolution of the AD converters might very well be a practical limitation in that regard for a digital receiver. Speaking, on the other hand, of an analog beamforming receiver, then, Well, it's clear that if we went back like a bit in time and sort of like a parabolic reflector that we could mechanically steer in some direction like this, then yeah, that would pretty effectively filter out jamming signals that came in from elsewhere, right? Now, if we do the analog beamforming in analog circuitry, I'm not so sure. I mean, there'll be all sorts of components. There'll be mixers, there'll be phase shifters, there'll be couplers, and they are not perfectly linear to start with. So if there's a strong jamming signal coming in, even from a different direction, I think this is very implementation dependent. But you're right. I mean, I think there's a great potential to explore whether analog beamforming or analog phase steering technology could be made more robust to jamming. So I think this is a bit of an open research topic where, as far as I know, I mean, the answer isn't fully known yet.
Yeah, and maybe you need like military grade hardware in order to do this.
It's possible. I mean, you know, it all depends on how much jamming power you won't be able to handle, right? Somebody is standing 10 meters from the base station blasting like a kilowatt of power, then good luck. Okay.
Okay, so what about these new frequency bands that we are moving into with 5G? Even if they are mostly in the like conventional bands right now, eventually we move to millimeter wave. Do you think that will cause new threats, or is it sort of the same ones?
Hard to say, I think. I mean, again, I think part of the answer will depend on how the actual circuitry is implemented, and I'm not entirely sure about this. But I mean, fundamentally, there wouldn't be a difference in, say, the susceptibility to jamming just because you double the carrier frequency or tenfold the carrier frequency. One thing that does happen is that with millimeter wave, you'll be able to form sharper, I mean, even in the angular domain, more narrow beams. So from that perspective, perhaps you could like more effectively also filter out jamming or offer additional protection. But it remains to be seen, I think, whether the electronics here offers the linearity and the resolution that would be needed to do such a thing.
Yeah, no, I was thinking that also that one thing might be that you have more bandwidth and then you could benefit from that.
Right.
And maybe the signals are going to be more spatially confined so that if you have a millimeter wave system in your home, that maybe the signals will not really make it out through the walls. And in the same way, jamming things from the outside might be hard to reach you.
Yeah, those are actually good points. I mean, you might be spreading over a larger bandwidth and you might have more directional transmission so that, I mean, with millimeter wave, you pretty much, either you have line of sight or you have nothing, right? So that's true. I mean, and you form very narrow beams. So it's possible that you'd gain also robustness from that.
Okay, so suppose we have a jammer in the system somehow. Could we detect that it exists? Is that something that is simple to do by processing the received signals?
Well, I mean, for one thing, it's definitely easy to detect that something is going on and something is wrong, right? I mean, if a communication link dies, it happened for some reason. Was it a fading dip? Was it a software malfunction? Was it a jammer nearby? So detecting something is going wrong is obviously real easy. Detecting whether it was a jamming signal, I think in principle, yes. I mean, we could, I think, easily think of algorithms that could detect and track the behavior of the link, the channel responses and all that, and say that, hey, look, something fishy is going on, it might be a jammer. Whether anything near that is implemented in like commercial products or systems, I don't know. I wouldn't think so. I never heard of it, in fact. But fundamentally, I think one could detect it. I believe the problem is rather that, suppose that we detect that there's jamming going on. Okay, bad luck. What are we going to do?
Yeah, I guess the military or the police could potentially send people to try to take out, so to say, the jammer, but maybe that doesn't make much sense for a telecom operator to try to have people stand by for doing that.
Yeah. Yeah.
So if you look more into the future, then would it be a way of building our network in a different way, change the architecture of how we put up the network equipment to make it more robust against jamming?
Well, I think my view is that we have to take this threat seriously, right? And it might seem a bit of sci-fi and futuristic or, unrealistic that we would at some point encounter large-scale jamming by some hostile actors. But on the other hand, if we look back in history, I mean, when the internet came around, I still remember, I think it was like 1994 or something, the first time I used the Mozilla browser. And then obviously folks working on internet technology at the time could very well think of and conceive of attacks like distributed denial of service and all of that. But nobody really probably thought that this is going to be mainstream in 2020, that hostile actors all over the globe are going to do all this to cause harm, right? So I think we stand with wireless technology in that regard about where the internet stood 25 years ago, that we can very well conceive of attacks that some terrorist organization or who knows, hostile other actor will really have the resources and competence to do this. It could buy like lots of small jammers that they deploy distributed over a larger geographical area and activated in some clever pattern. It'd be extremely hard to disarm them or even locate where they are. So I think in that regard, the threat here is a little bit like distributed denial of service was 25 years ago, right? So we have to, I think, prepare and build a society and build an infrastructure that could handle attacks like that. So I think that we ought to invest in looking at, for example, could we build into the forthcoming standards some ultra robust communication mode where maybe data rate isn't as important. It's not, the important thing is not that you and me can sit here and talk and see each other in HD video in real time, right? The important thing is that we can communicate at all in case something happens. Somebody deploys all these distributed jammers. I mean, think of an autonomous drone just dropping small jammers with a small parachute, and they land at random places all over town, or just land in the trees somewhere, and they send sporadic signals that jam the control channels of the 5G network. Nobody can talk to anyone. No infrastructure, no wireless services. I mean, paying for the parking might be the smallest problem here, right? So I think, yes, we have to invest in making our wireless systems, and this also goes for the commercial systems, not only more bandwidth efficient and high rate and all that, but also more robust to possible intentional attacks.
Yeah, it will be interesting to see now how things are developing. So I think in Sweden, sort of the police officers have had their own cellular system in a completely different frequency band, and now there are discussions whether 5G technology is going to be utilized by the police as well. And then sort of the threat against the network will also potentially be increasing. So it will be interesting to see what is going to happen. So before we wrap up, I was thinking that we could talk about one more thing, which is what we are using wireless signals for, that's not directly communication related, but it's still something that we do maybe every day, depending on how good geographical sense you have, namely positioning, using the GPS to let the phone position ourselves and tell us where to drive. So when it comes to wireless positioning, are there sort of active attacks against that as well?
Definitely. I mean, there are jamming and spoofing attacks on GPS, just like there is on wireless, right? And jamming is the simplest, and the very simplest of the simplest is like small jammers that you can buy for the car and plug into the like cigarette lighter outlet in the car, and they jam your GPS. And the main air quotes use case for that is the truck drivers who don't want their employers to know how many hours a day or where they are, or thefts, right? If someone steals a vehicle and wants to drive it across the border and disappear with it. Jamming is obviously more sophisticated, but there are also examples of that where jammers used. I think it was in the Persian Gulf somewhere where the GPS was spoofed so that ships were misled. They were misled about their position. And
was this
is a reality.
Swedish
it already happens.
ship Stena something that was British flagged that was sort of suspicion that it was tricked into Iranian water so they could stop it.
Yeah, I think the story was something like that. I mean, this is a real world example that this is already going on. I mean, probably by actors who have a lot of resources and apparently some competence to do the job. But you're entirely right that society is becoming increasingly reliant on wireless infrastructure for communication. Yes, we are also increasingly reliant on infrastructure for wireless positioning, I mean, GNSS services in particular, right? And this is, I think, another threat that we have to take extremely seriously. And it might be one thing if your GPS is jammed so you don't find a way home or the way in town. I mean, it might not be a big deal, right? But GPS is also used for a lot of other services like time synchronizing wireless base stations, for example, and then jamming the GPS system itself could cause a lot of harm on the wireless communications infrastructure that way too.
Yeah. I've been thinking about this sometimes when people talk about autonomous vehicles, they're sort of implying that we're going to have a wireless control of them so that somehow the intelligence is in the cloud somewhere, which sounds incredibly stupid because if you jam the signal, what should the car do? Then it needs to have its own intelligence. And can it really rely on having a GPS signal that tells it where it is? Or is it just like anyone else that if you don't have a GPS, you need to look around and try to assess where you are and drive in a safe way?
Yeah, that's a great point. I mean, it sounds like Christmas Eve for anyone into sabotage, right? You drive up nearby one of these autonomous vehicles and you jam the relevant frequency bands and the car has no idea what to do. So I suppose the only thing it could do is to slam the brakes and then you'd had some fun. I don't know, but you're certainly right. I mean, we are building, again, an infrastructure that's extremely susceptible to this sort of attacks.
So I hope that with this episode we have sort of made more people aware of these potential threats, and that in the future the networks and the new autonomous vehicles and all kinds of systems are going to be built in a way where this type of robustness is in the mind of designers. Yeah,
I also hope so. Thanks a lot. Thanks, Emil. It's a great discussion.
Thank you for listening to this podcast, and then please subscribe or send us questions, and we might base future episodes on your questions as well. So thank you.
Thank you. Bye-bye.